It is impossible to visualize the scale of the universe. There are roughly 2 trillion galaxies. 2 trillion. 2,000 billion galaxies.
How old is our universe? It's a question that has vexed scientists for ages. It is simple enough, but as the years go by, it's become apparent that settling on the answer isn't quite so easy. Even today, the matter remains open for discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. Indeed, that's exactly what happened last week when a new study based on James Webb's data was released, challenging the long-held notion that our universe is nearly 13.8 billion years old. The groundbreaking new study suggests that our universe could be twice as old, shattering the dominant cosmological model, while also reconciling the enigmatic, impossible early galaxy problem. But is such a bold claim really possible? Join us today as we dig deep into this shocking discovery and what it means for our understanding of the cosmos. One of the most revelatory facts about the universe is that we actually know how old it is, 13.8 billion years. If we could step back in time, though, we'd find that the universe as we know it was a very different place early on. The modern stars and galaxies we see today came about from a series of gravitational mergers of smaller mass objects, which consisted of younger, more pristine stars. At the earliest stages, there were no stars or galaxies. Looking back even farther, we come to the hot Big Bang. Today, astronomers and astrophysicists who study the early universe confidently state that the age of the universe, with an uncertainty of no more than less than 1%, a remarkable achievement that reflects the discovery of our universe's birthday. But how did we get there? In fact, we have 2 ways of measuring the age of the universe, and they're both compatible with this figure. Method 1. Tracing back the history of the universe. The first way we estimate the age of the universe is actually the most powerful. The starting point goes all the way back to the 1920s, when we first discovered the expansion of the universe. In physics, if you can uncover the equations that govern your system, i.e. the equations that tell you how your system evolves over time, then all you need to know is what the system is doing at any particular moment in time, and you can evolve it as far back into either the past or future as you like. As long as both the laws of physics and the contents of your system don't change, you'll be all right. In astrophysics and cosmology, the rules that govern the expanding universe come from solving general relativity for a universe that is, on average, filled with equal amounts of stuff everywhere and in all directions. We call this a universe that's both homogeneous, meaning the same everywhere, and isotropic, which means the same in all directions. The equations you get are known as the Friedmann equations, after Alexander Friedmann, who first derived them, which have been around for a full 99 years now. That's since 1922. These equations tell you that a universe filled with stuff must either expand or contract. The way the expansion or contraction rate changes with time is only dependent upon 2 things. Firstly, how fast the rate is at any point, such as today, and secondly, what exactly your universe is filled with at that particular point. Way back in the early days of cosmology, people used to joke that cosmology is the search for 2 numbers, implying that if we could measure the expansion rate today, what we know as the Hubble parameter, and how the expansion rate changes with time, what we called the deceleration parameter, which is a horrible misnomer because it's negative, the universe is accelerating and not decelerating, then we'd be able to determine precisely what's in the universe. In other words, we could know how much of it was normal matter, How much was dark matter? How much was radiation? How much was neutrinos? How much was dark energy, etc., etc.? This is a very nice approach because they're simply reflective of the two sides of the equation. The expansion of the universe and how it changes are on one side, while the matter and energy density of everything is on the other side. In principle, measuring one side of the equation will tell you the other. You can take what you know and extrapolate it back in time to when the universe was in the very hot, dense, and small volume state that corresponds to the earliest moments of the hot Big Bang. The amount of time that it takes you to wind the clock back from now until then tells you the age of the universe. In practice, though, we use multiple lines of evidence to all complement one another. By bringing multiple lines of evidence together, we can put together a consistent picture that folds all of these measurements together. Some of these are particularly important, such as point. The large-scale structure of the universe tells us the total amount of matter that's present, as well as the normal matter-to-dark matter ratio. Point. The fluctuations in the cosmic microwave background relate how quickly the universe is expanding to a variety of components in the universe, including the total energy density. And point. Direct measurements of individual objects, like type Ia supernova, at a wide variety of distances and redshifts can teach us what the expansion rate today is and can help measure how the expansion rate has changed with time. What we end up with is a picture where the universe appears to be expanding at a rate of less than plus or minus 67 kilometers per second per megaparsecs today, made of 68% dark energy, 27% dark matter, 4.9% normal matter, about 0.1% neutrinos, and less than 0.1% of everything else, such as radiation, black holes, spatial curvature, and any exotic form of energy not yet accounted for here. Put these pieces all together, and the rate of expansion today, and the various contents of the universe, and you get an answer for the age of the universe, 13.8 billion years. The other way astronomers estimate the age of the universe is by studying global clusters. Global clusters are a dense collection of roughly 1 million stars. Since all the stars in a global cluster formed at roughly the same time, they can serve as cosmic clocks. This way of estimating the age of the universe is based on our understanding of the life cycle of stars. The life of a star depends upon its mass. High-mass stars are much brighter than low-mass stars. They rapidly burn through their supply of hydrogen fuel. A star like the Sun has enough fuel in its core to burn at its current brightness for approximately 9 billion years. A star that is twice as massive as the Sun will burn through its fuel supply in only 800 million years. A 10 solar mass star, a star that is 10 times more massive than that of our Sun, burns nearly 1,000 times brighter and has only a 20 million year fuel supply. Conversely, a star that is half as massive as the Sun burns slowly enough for its fuel to last more than 20 billion years. So, if a global cluster is more than 10 million years old, then all of its hydrogen-burning stars will be less massive than 10 solar masses. This implies that no individual hydrogen-burning star will be more than 1,000 times brighter than that of our Sun. If a global cluster is more than 2 billion years old, then there will be no hydrogen-burning stars more massive than 2 solar masses. When we observe global clusters, we find that we have a wide variety of ages, but only up to a maximum value 12-something to 13-something billion years. Many global clusters fall into this age range, but here's the important part. None are older. For both individual stars and stellar populations, to the overall properties of our expanding universe, we can derive a very consistent age estimate for our universe, 13.8 billion years. If we tried to make the universe even 1 billion years older or younger, we'd run into conflicts on both accounts. A younger universe can't explain the oldest global clusters. An older universe can't explain why there aren't global clusters that are even older. Meanwhile, a significantly younger or older universe can't accommodate the fluctuations we see in the cosmic microwave background. Put simply, there's too little wiggle room. That's why the general consensus among scientists is that the universe is roughly 13.8 billion years old and ever expanding. However, the study published July the 7th in the journal Monthly Notices of the Royal Astronomical Society seems to confirm that previous estimates were widely off. What's referred to in the new study as the impossible early galaxy problem has long baffled scientists who struggle to reconcile why some galaxies thought to have come into existence long after the Big Bang appear to, in fact, be much older than the universe's estimate age. Observed through NASA's James Webb Space Telescope, galaxies and stars like the Methuselah appeared to have a level of maturity and mass typically associated with billions of years of cosmic evolution. It's a notable observation, considering the widely held belief that they came into existence hundreds of millions of years after the Big Bang. According to Rajendra Gupta, an adjunct professor of physics at the University of Ottawa, these puzzling observations can be explained by the fact that our universe is actually much older than we thought. Gupta's study introduces a novel model which stretches the galaxy formation time by several billion years, making the universe 26.7 billion years old, or twice as old as it generally was accepted. This model incorporates Fritz Zwicky's tired light theory, which suggests that the redshift observed in light from distant galaxies is a result of gradual energy loss over vast cosmic distances. According to Zwicky, light simply gets tired as it travels vast distances across the cosmos. This is in stark contrast to the current established theory that says the observed redshift of distant celestial objects, such as galaxies, is primarily due to their motion away from us, a consequence of the universe expanding in all directions. However, the Swiss astronomers' tired light theory faced significant controversy within the scientific community. One major challenge was that tired light would not only cause a redshift, but also a significant decrease in the intensity and brightness of the light. Critics argued that if light lost energy over cosmic distances, the observed brightness of distant objects would be much lower than was actually observed. Additionally, Zwicky's theory, which was first proposed in the mid-20th century, conflicted with the discovery of the cosmic microwave background radiation. This radiation is uniform across the sky and represents the residual energy from the Big Bang, providing strong evidence for the expanding universe theory. Although Zwicky's theory initially conflicted with observations, Gupta proposes a fresh perspective by allowing the tired light theory to coexist with the expanding universe. The redshift phenomenon can be reinterpreted as a hybrid phenomenon, combining both expansion and energy loss, Gupta says. This new interpretation offers a plausible explanation for the early galaxy observations. In addition to the tired light theory, Gupta introduces the concept of evolving coupling constants, proposed by physicist Paul Dirac. Coupling constants are fundamental physical constants that govern particle interactions, and Dirac suggested that they may have varied over time. By allowing for the evolution of these constants, Gupta's model extends the time frame for the formation of early galaxies observed by the James Webb Telescope. Instead of a few 100 million years, this revised framework allows for several billion years of cosmic evolution, offering a more satisfactory explanation for the observed advanced development and mass of these ancient galaxies. Gupta's model also challenges the traditional interpretation of the cosmological constant, which represents dark energy driving the universe's accelerating expansion. Instead, he proposes a modified constant that accounts for the evolution of coupling constants. This adjustment in the cosmological model may help to address the perplexing puzzle of small galaxy sizes observed in the early universe, leading to more accurate observations and a deeper understanding of cosmic evolution. While Gupta's model is a radical departure from the prevailing cosmological framework, it presents a compelling case that warrants further investigation. By marrying the expanding universe theory with Zywicki's tired light hypothesis and incorporating evolving coupling constants, Gupta offers an intriguing solution to the mysteries surrounding early galaxies and the age of our universe. Regardless, no one can't deny that there are some problems with the new model. The first is that tweak theories are weak theories. While this model can be made to fit observational data, there's no physical motivation for doing it. There are lots of models that can be tweaked to fit the data, which is not the same as having a robust physical model. The author of the work argues that there could be some underlying mechanism that causes tired light and the physical constants to shift in just the right way, but there is still a lot of fudging in the model. The second problem is that JWST's observations don't rule out the standard 13.7 billion-year-old universe. The galaxies are more complex than some computer simulations have predicted, but that's not surprising given the limits of large structure models. There are plenty of ways early galaxies could have evolved quickly that don't require rewriting cosmology altogether. But even without a strong physical motivation to create this model, the work is still useful. It's the kind of paper that thinks outside the box, which is a great way to make sure we aren't locked into old models just because they've worked so far. It isn't likely that this new model overturns standard cosmology, but as long as ideas are testable and disprovable, as this model is, there is no harm in adding it to the pile of ideas. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on any future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we'll see you next time.